Okay, so the last time we were speaking about entailment for OWL, and we spoke about how we can reduce entailment to undecidability. This is not just for OWL, this is a common property for various types of logics. So the question then is, how can we implement unsatisfiability. So we said we can reduce entailment to unsatisfiability, which is basically checking if an ontology is consistent or not. And then we asked, how can we decide that? How can we implement implement unsatisfiability? And what we said is that it's an undecidable problem, and we mentioned the COLLATZ conjecture, which is this notion that this type of Java program, there's a conjecture that this type of Java program will terminate no matter what input is given here. So essentially, we multiply odd numbers by 3 and add 1, and we divide even numbers by 2. And for all of the known values that we have, we know that it returns to 1, the positive integers. But in general, there's a question mark over whether or not this is the case for all integers, or if it can somehow form a cycle that doesn't reach 1, for example. So this is unknown, and this is one of the considered an extremely difficult topic that we're nowhere close to solving with modern mathematics. So this is an unsolved problem in mathematics, and if we knew that this program terminates, this problem would be solved, which is to say that if we had a solution for the halting problem, then we could address this, we could answer this question. So the halting problem is, again, this idea that we have a program, something you could write in Java or Python, or if we wanted to be more formal, a Turing machine, and we have an input to that program. And the output of for the problem is true if the program halts on that input, if it will eventually stop, or false otherwise if it somehow continues forever, runs forever and will never stop. So this problem is undecidable. So it means that we can't implement this function to implement this to solve this problem. A general algorithm to solve the halting problem does not exist. So it will halt for it will not halt for all program input pairs. So in some cases, yeah, we can pass the program in an input, and we can, for example, just run the program with the input and wait a bit, and after 2 seconds it stops, and then we can output true, right? But the problem is that in some cases, what happens when we give it a program and an input for which the program won't halt? Well, that strategy won't work, right? It won't work because we'd have to run it forever to see if it runs forever, right, somehow. So the question is there some clever way in which, for those sorts of cases, we can implement something to check whether or not a program halts or not? And the answer is no, there is no clever way to do that. And how this is proven, just as a sketch, is just that if we had a solution to the halting problem, like a function halt, we could we could create this tricky program, this tricky code that uses this function. So we could essentially ask you, in our tricky program, we could ask the halting problem, does the tricky program itself or a copy of it halt? Yeah. And if it says true, then we just loop forever. Okay, so essentially we don't halt. And if the halting problem says false, it says yes, our tricky program will halt, will not halt. It will continue forever. Then we stop. So essentially, in this tricky program, we ask the halting program what it's going to do on the tricky program itself, and then we contradict it, right? And this is a valid procedure, because if this is decidable, then this is essentially, you could implement this in Python, right? This logic. So this again is a valid program. If somehow we had a program for assuming that we had a program, an implementation for the halting problem here. So this means that it's a paradox. Effectively, if it were possible to have this, we would create this impossible program that contradicts the implementation of the halting problem. So this means that no such thing can exist because we create this paradoxical situation. So we know that certain things we cannot implement. There's just no way to implement these problems in code. So okay, let's take the specific problem instance for the halting problem. So the COLLATZ halting problem. So we have an input, which is none. We assume that we don't need an input, it's a null input. And we're going to output if the following. We're going to output true if a COLLATZ program halts on all inputs and false otherwise. So we're going to try to use, our problem is essentially to figure out what mathematicians can't, which is, does the COLLATZ program halt on all possible integers, positive integers? Is this problem decidable or undecidable? What do you think? So we don't know. Okay, this is a kind of a trick question. So this problem is decidable for sure. We know this is definitely a decidable problem, and it's a decidable problem because one of these outputs is correct, right? So there's two implementations we could consider, two possible implementations. We could just return true or we could return false. So one of these implementations is correct because one of these must be the answer, right? So somehow one of these things must be a solution to this problem. So even though we don't know which of them is the correct solution, there is a solution to this problem, and therefore the problem is definitely decidable. So this is why I say, just to give an example of why the halting problem is undecidable in the general case for all programs and inputs. So there is a generalized version of the COLLATZ program. There's a generalized version of this problem that's known to be undecidable, which is basically in the COLLATZ program, we multiply by 3 and we add 1, and we do a modulo 2, or we divide by 2. So if we generalize that function and allow the certain values to be changed and input into the program, and then we ask, does the COLLATZ program halt on for these particular parameters, then that problem is known to be undecidable, for example. Okay, so there is another more intuitive maybe problem that's often used for proofs. It's the domino tiling problem, and it's quite a nice, or at least I like it, undecidable problem. And it's quite commonly used in proofs to say that something is undecidable. So let's talk about the domino tiling problem first. We have a set of dominoes like D, which essentially indicate us 4 colors effectively: a left color, a bottom color, a right color, and a top color. Yep. So we have D, or set of dominoes like this. And what we need to do in this problem, given that set of dominoes, is output true if there exists a valid infinite tiling, like we see here with T, or as we have started at least with T here. Otherwise, we should return false if there's no way to put these tiles of these dominoes together to create an infinite tiling. Of course, we can use as many copies of a particular domino as we want. So, okay, is it possible in this case? Obviously, if we had, for example, a domino that was red on all 4 sides, that would be trivially true, right? Because we just have red all the way to the right, all the way to the top, and all the way to infinity. What in this case, is it possible? Well, at least I tried to, maybe there is some sort of periodicity, or maybe there's some way to generate an example here, but at least to me, looking at the slide, it's not so clear that there exists a way to continue infinitely tiling. So this problem, in fact, is this problem decidable or undecidable? I already answered that question. This problem is known to be undecidable. So there are variants of this problem as well for a board of finite length. So for an exponential size board, or different types of, and that gives different types of complexity. If the board is finite, of course, this problem is decidable because you could just try all the possible combinations, for example. But if it's an infinite tiling, then this problem is undecidable. So how do we know this? Because some people showed that you can represent the halting problem, you can reduce it to a tiling problem. So given an instance of the halting problem, you can actually rephrase it as an instance of the tiling problem. This means that the tiling problem is undecidable, right? So this means essentially a Turing reduction just means that we can write a program that reduces from one to the other. And the program somehow has some certain properties. So it will always return an instance of the domino tiling problem. So essentially it says that it's a program that will always, given an instance of the halting problem, can always reduce that instance to an instance of the domino tiling problem. So based on this, we know that the tiling problem is undecidable, right? Why is that? Because if the tiling problem were decidable, and if we have this type of Turing reduction here, this nice reduction that will always guarantee to turn any instance of this problem here into this one here, then this would be decidable. Because for any instance here, we just apply the reduction and then we have a decidable problem. So obviously this is not possible because we already know this is undecidable, right? So since we know this is undecidable, we know that we can't implement this, and therefore this means that our assumption here that this is decidable is a contradiction. Okay, so there's no way we could do that. Again, if we could, it would mean that the halting problem were decidable if this were then decidable. So in a similar way, we can reduce from undecidable problems to OWL entailment. So that way we can prove that we can never somehow solve the problem fully of OWL entailment. So it means that we can, for example, define a reduction from the domino tiling problem to OWL entailment. We can also define a reduction from the halting problem to OWL entailment as we described. So here we reduce from an instance of the problem of does D have an infinite tiling to the question of does an OWL ontology O entail an ontology O prime? Or is an OWL ontology satisfiable or not? We could also have here, that would be enough. So in the next class, just to talk about this reduction, as it's an interesting example of how we know in computer science theory, kind of what is possible and what are the limits of computation and so forth. We'll talk about how we can encode this. It's also a nice way it's kind of a nice exercise for OWL. It's kind of how can we express this in OWL? It's an interesting exercise, and it's not that difficult, although there's some tricky bits. So we'll talk about that in the next class, and then we'll talk about, essentially we'll show that you can reduce this, and then we'll say, okay, in that case, if we can't implement somehow entailment for OWL, what do we do? What are the solutions? Any questions or doubts? One last comment is just that this is not specific to OWL. This is there's also similar results for first order logic. It's a general kind of principle of knowledge representation that if we represent knowledge, for example, in this case using OWL ontologies, and we axiomatize or try to define for machines the semantics of the knowledge and get the machines to start reasoning about the knowledge, there are limits to what machines can do. Or to what we can implement with algorithms. So otherwise, knowledge representation, we could represent things in mathematics, for example, and ask them, are these results true? So there are limits to this process. Yep, Pablo?
Yeah, I have one question. Before you showed like a problem that is decidable, like but I did not understand. So can you explain?
Sure. So this is kind of a trick problem. There's also a similar question, which is the problem here is that there's no input. So we'll explain the problem. We have this problem, which is no input. And the output should be true if and only if the COLLATZ program halts on all inputs, which is to say true if it halts on all inputs and false otherwise. Do you remember the COLLATZ program?
Not so much.
Okay,
Maybe.
so we'll go back to, we can go there. So this is the COLLATZ program. It's written in Java. And it's an open problem in mathematics whether or not this this program will ever stop. So what it does is effectively it has three parts here. First of all, it will halt or return if n is equal to 1. So once we reach 1, we stop. Otherwise, if n is divisible by 2, if it's even, then we call the function on itself dividing n by 2. So if n were 4 here at the start, then it will call itself with 2 in the next step. Or if we were 16, it will call itself with 8 and so forth. Or if we're 6, it will call itself with 3. And the last step is if it's odd and it's not 1, then it multiplies n by 3 and adds 1. So at some steps it goes down and in other steps it might go up. Yep. And the unresolved problem in mathematics is whether or not this program will halt no matter what integer, not just a 32-bit int, but any positive integer. So to take an example, we have input 6. So since this is even, divided by 2 is 3. Since it's odd, multiply by 3, add 1, 10. Since it's even, divide by 2, 5, and then 16. And then once we reach a power of 2, it will just drop immediately to 1. And this problem is not known to, it's an open problem. It's called the COLLATZ conjecture. It's a very difficult problem in mathematics, and people think we're nowhere close to being able to answer this with modern mathematics. So then, of course, if we had this halting problem, if we had a solution to the basically saying whether or not any program will terminate on any input, any valid input for that program. If we had a solution to this, we could somehow resolve the COLLATZ conjecture, right? We could actually just use the halting problem and say, does this thing terminate? Yeah. Does this program here terminate? And this seems okay. This is mainly a kind of an example to illustrate that actually, well, in some sense, this is a decidable problem, right? So because we can implement this by just simply returning true or returning false. And one of these implementations is perfectly an implementation for this because the result is either true or false. Even if we don't know which one it is, the problem is then decidable. So it's the point that it's only undecidable in the general case. So that if we had something that could kind of, if the problem were to decide whether or not the general form of COLLATZ problem were to terminate in each case for every integer, then that problem would be undecidable, for example.
Yeah, I understood.
Yep. Okay. Any other questions or comments? Okay, so machines are not all powerful. Yes, we can go to Discord. Just to mention that most of the lab today, we're going to focus this time on class definitions and class axioms. Most of it comes from, the most useful class for you will be class 4, since we're now in more kind of conceptual topics. In class 4, you have the examples of the features that we'll be using in the lab. So yeah, you can look at class 4. There might be some useful information in class 5, but mainly you'll need to refer to class 4. Okay, so see you in the Discord.